Okay, is my screen visible?
Yes, sir.
Yes, sir.
Okay. So we were talking about the bases. Okay. So we could have a linear vector space. A linear vector space is spanned by a basis, a set of basis vectors. And when I say vector, remember when I say vector, we are talking about functions. Okay, vectors means functions. Okay, so we are talking about a set of functions. Okay, so that's the basis. So we have a set of vectors, and these vectors also they belong to the same vector space, and this set of vectors are phi 1, phi 2, and so on, such that any member of this vector space, can be written in terms of the basis vector. And by the way, this is the Einstein's summation convention. Here I is a dummy index because it has been repeated. Any index that gets repeated is a dummy index. That means the summation is implied. Okay, that means there is a summation over I that is understood. Okay, so that basically is your basis. Okay, that's the basis vector of a vector space. All right, so now let's take an example. Okay, example of, we'll consider a vector space which is spanned by a basis comprising of the following three functions: p0, p1, and p2. Are you all familiar with these functions? This p0, p1, and p2. This p0, p1, and p2. Are you all familiar? Pn of s. What are these? These are your familiar
Legendre.
Legendre polynomials. Okay, these are your familiar Legendre polynomials. So Legendre polynomial p0 is 1, p1 is s, p2 is equal to 3 by 2 s square minus half. Okay, so these are your Legendre polynomials. So these Legendre polynomials, they form a basis. These three Legendre polynomials, they form a basis. Okay, so any quadratic form of S would be a function of this vector space. Any quadratic form of S, quadratic form means S square, any function which contains S square, the highest degree is 2. Okay, the degree of that is 2. Any polynomial function whose degree is 2. Okay, that is a quadratic form. So any quadratic form would be a function over this of this vector space. So an example, okay, so what we need to do is we need to express the following functions in terms of this above basis. This basis p0, p1, p2. We want to express these functions. Okay, so what I'm going to do is let me take an example. I'll do problem number 4. Okay, I'll do problem number 4. So let me quickly grab this. And let me do question number 4. Let's do this problem. So this is our basis. Okay, and we need to write down this function that is f of s in terms of p0, p1, and p2. Okay, so the way to do that would be something like this. So we have here this p0, p1, and p2. So we can write it like this. Okay, so p0, p1, and p2. The first this function. Okay, we have f s square minus s minus 6. So if I say let's say 1. Okay, 1, it can be written in 1 is nothing but your p0, right? Here we have p0 is equal to 1, and just move them around a little bit. Bring the 1 here, p0 goes over here. Put the 1 here and p0 over here. So 1 is equal to this one. So how we can write is like this. P0, bring in P1 also and P2 also. P1 as well as P2. P1 and P2. So what we can do is this entire thing. because 1 is P0 is equal to 1, so we can say that 1 into P0 plus P1 is, there is no P1 here, right? Because it is only 1, so 0 into P1 plus 0 into P2. That means this 1, okay, this 1 can be written as in terms of the coefficients. And what are the coefficients? Because these Legendre polynomials are already known to us, this and this, they're already known to us. So what are the coefficients? The coefficients are 1, 0 and 0. So you can just write this as 1 comma 0 comma 0. Okay, we can write it like this. Next, what about S? What about S? In a similar way, from here we have P1 equals S. P1 equals S. So again, like before, move this here and bring this over here. So what is S equal to? S is equal to P1. So let's place the P1 over here. Let's bring in P0 and P1, P2 also. So P0 and P2, which they were not there earlier. So multiply this with 0, multiply this also with 0, and there is a P1 here, multiply this with 1. So this S, this function S can be written as 0, 1 and 0. Is this understood? Is this understood? 1. So this function 1 can be written as 1, 0, 0. S can be written as 0, 1, 0. Is that clear to everyone?
Yes, sir.
Okay, so now the challenge for you is this. What about S square? How do you write S square? Use these two. Use these two ideas. Can you try this for yourself? How do you write S square? Please try this. If you have a notebook, please try this out. I'll give you a couple of minutes. Please try this out. At least you can tell me what kind, how you're going to proceed. Okay, you can tell me that also.
Sir, 1 by 3 is 0 and 2 by 3.
Very good. Excellent. Okay. So we start from here. The way to do that would be we start from here. So we have P2 is equal to 3 by 2 S square minus 1 by 2. So over here, this because we want S square, right? So S square, we bring it on this side, and P2 we bring it over here. So when you get this here, this will become plus, right? So we'll get a plus here, with a plus here. Then multiply this throughout by 2 by 3. Okay, so multiply this throughout by 2 by 3. Take the reciprocal, 2 by 3, multiply P2, multiply this with P2. In a similar way, this 1 by 2 also, you multiply this with 2 by 3. And when that happens, this 2 and 2 gets cancelled. Okay, this 2 and 2 gets cancelled, this 2 and this 2 will get cancelled, and what will be left behind is 1 by 3. Okay, this is what we have, but this sorry, okay, so this 1 by 3 is what is left behind, and there is a P2 here. Let me get this P2 somewhere here. This 1 by 3 is over here. This 1 by 3 into 1, okay, 1 by 3 into 1. So what I can do is 1 by 3 into 1, and 1 is nothing but P naught. 1 by 3 into 1, and this 1 is nothing but P0. So I'll just put a P0 here. Okay, and then we have P0 and P2. We have P0 and P2. So what is missing out here is P1. What is missing out here is P1. So we can always bring this P1 and multiply that with 0. Okay, and we get this. And who told me the answer? Who was that? Who told me the answer?
Sir, me.
Yeah, who is
Sir,
me?
Korabi.
I can't see. Korabi. Okay, good job. So this is going to be equal to 1 by 3, comma, 0, comma, 2 by 3. Understood? So this is S square. S square can be written as this set of coordinates. S can be written as this set of coordinates, and 1 can be written as this set of coordinates. So here the function that we are talking about, this function. So therefore, this function f of small s, f of s is equal to s square minus twice s minus 6. I just substitute this s square, replace it with this one. So 1 by 3, comma, 0, comma, 2 by 3. This is your s square minus 2 into s. And what is s? S is 0, 1, 0. And minus 6 into 1. 6 into 1. 1 is 1, comma, 0, comma, 0. So this will be equal to 1 by 3 minus 0. Okay, this is going 2 times 0 is 0 minus 6. That's the first coordinate. Then 0. Okay, minus 1 minus 0. So we'll have minus 1. And the last one will be 2 by 3 minus 0 minus 0. So 2 by 3. Okay. So what will this turn out to be? Even did I go wrong? Oh, my mistake. Think this should have been minus 2, right? Because this is 2 times 1. 0, 2 times minus 2 times 1, minus 6. Yeah, this should be minus 2. This should have been minus 2. All right. So what do we get? The first one, 1 by 3 minus 6. 1 by 3 minus 6 is minus 17 by 3. Just check. Is it correct? Is it correct?
Yes, sir.
Minus 2. And last is 2 by 3. All right. So whatever you have here, this is supposed to be multiplied with P0. This is supposed to be multiplied with P1. And this is supposed to be multiplied with P2. So therefore, we have this function which is given to us in terms of, what are you supposed to do? You are supposed to write down this function in terms of the Legendre polynomials, that is P0, P1 and P2. So this will be simply equal to, just get these coordinates. So it will be minus 17 by 3 into P0 minus 2 into P1 plus 2 by 3 into P2. So that's how we write down this function in terms of the Legendre polynomials. So you can see here, I'm able to write this function. in terms of the Legendre polynomials P0, P1 and P2. This is a quadratic function. It's a quadratic function because the degree is 2. So all quadratic functions, all quadratic polynomials can be expressed as a linear combination of the Legendre polynomials P0, P1 and P2. All quadratic polynomials can be expressed in terms of as a linear combination of the Legendre polynomials P0, P1 and P2. Okay, so P0, P1 and P2. So we say that the basis P0, P1, P2 spans the linear vector space of all quadratic polynomials. The basis P0, P1 and P2, it spans the linear vector space of all quadratic polynomials. Is this clear? Is this clear to everyone? All right, please try the others. Okay, 1, 2 and 3 are very easy. I already did. Instead of 4 I did 1, right? So whatever I got, you just multiply it with 4. The others also, please do this. 5 and 6 also, please do that. Okay, any questions so far? Okay, let's take another example, a vector space. So here this was a finite vector space. Okay, the basis contained a finite number of functions. The basis was P0, P1 and P2 alone. Now let's consider a scenario where the vector space is spanned by members. Okay, there are infinite series. Okay, let's take an infinite series. Okay, so in that case, so let's say I have a basis whose members are these infinite elements in the basis. So phi n is equal to s to the power n equals 0, 1, 2, 3 and so on. Okay, 1 second. All right, so we have this one. So phi n is this, so you can just see for yourself what is phi 0. When you put n equal to 0, what is phi 0? Phi 0 is equal to s to the power 0, which is 1. What is phi 1? What is phi 1? Phi 1, s to the power 1, which is s. What is phi 2? S to the power 2. What is phi 3? S cube, and so on. So each of these, powers of s, that is basically the basis. Okay, so members, the functions which have a Maclaurin series representation, all functions which have got a Maclaurin series representation. Quick recap: what's a Maclaurin series? What's a Maclaurin series? What is a Maclaurin series? Anyone? Anybody? Maclaurin series? Yes? Angeline? Are you there?
Yes, sir.
Yeah, what's a Maclaurin series? What is a Maclaurin series? Angeline, do you remember? Adelphi, are you there? Adelphi? Adelphi? Urban, are you there? Urban?
Yes, sir.
A series expansion, sir. A series expansion centered about 0.
Series expansion. Okay, it's a Taylor series expansion. Maclaurin series is a special case of the Taylor series expansion. About
0, sir.
Yes, it's a Taylor series expansion about x equals 0. So that's your Maclaurin series. Okay, so we can actually the vector space, all the functions which have got a Maclaurin series representation, all the functions which have got a Maclaurin series representation, all those functions can be spanned by this basis. All this can be spanned by this basis, and you can check for yourself. For instance, that exponential function e to the power s. What is e to the power s? What is e to the power s? What is the Maclaurin series expansion? The Maclaurin series expansion, by the way, this is summation s to the power n by n factorial, right? N equals 0, 1, 2, 3, 4, and so on. So that means 1 plus s square by 2 factorial plus s cube by 3 factorial and so on. And you can see here, this is nothing but your phi 0, right? 1 is nothing but your phi 0. So no, 1 is nothing but your phi 0. Then s is nothing but your phi 1, right? S square is nothing but phi 2 by 2 factorial. S cube is nothing but phi 3 by 3 factorial and so on. So in other words, this can be written as this kind of a summation. This summation, that is 1 by n factorial into phi n, this kind of a summation. So this is the coefficient, these are your coefficients. So that means e to the power s, if you want to write this in terms of, without writing each of these basis element, without writing these basis elements, you could write this as 1 comma 1 comma 1 by 2 factorial comma 1 by 3 factorial comma and so on. Just like, I mean, if you want to write it in this way, if you want to write this in terms of its components, in terms of its coordinates, if you want to write it like this, you can write it in this way. Only difference is here we were having finite number of coordinates 1, 2, 3, and in this case we have infinite number of such coordinates. So that means each of this function, we can write this, we can express this as in terms of this basis. Okay, so this basis, it is a basis for all the functions. So which is the linear vector space? So the question here is this. Okay, right, let me get the other one. For example, cos. Okay, cos is basically your even functions, right? Cos, how do you write down cos? The Maclaurin series expansion of cos x. What is Maclaurin series expansion of cos x? 1 plus x square by 2 factorial plus x to the power 4 by 4 factorial. Oh, sorry, this is plus and minus, alternating plus and minus. So we have 1 minus plus minus plus and so on. So if I replace this x with s, so we will have cos s is equal to s square, 1 minus s square by 2 factorial plus s to the power 4 by 4 factorial and so on. So this s square s to the power 4, we can write it as phi 2, phi 4, and there is a 1 here, that is phi naught. So we can write this cos in terms of this. So these are the coefficients. So cos s, how can you write down cos s in component form? How can you write down phi 0? What is being multiplied? 1 is multiplied. Phi 1, do we see a phi 1 here? Do we see phi 1 here? We don't see phi 1. If you don't see phi 1, put a 0. Do we see phi 2? Yes, we see phi 2, and we put 1 by 2 factorial. Do we see phi 3 here? There is no phi 3. Since there is no phi 3 here, we will just place a 0. There is no phi 3, so this means this is 0. Do we see a phi 4? Yes, we see a phi 4. This is going to be plus 1 by 4 factorial and so on. Okay, so that's your cos. Is this clear? Lastly, sine. Okay, sine will be the other way around, right? It will be even functions. So here also the same thing. Sine contains only the even functions. So you can see here, this one is your, right, phi 1, that is x, right, or s minus s cube by 3 factorial plus s to the power 5 by 5 factorial. So s cube, s to the power 5, these are from this basis here. So what will be the expansion of sine s? Sine s will be equal to sine s. We can just write this as sine s will be equal to, do we see a phi 0? We don't see a phi 0. In the expansion, we don't see a phi 0, so it will be 0. Do we see a phi 1? Yes, we see a phi 1. What is being multiplied with phi 1? 1. Do we see a phi 2? We don't see a phi 2, so 0. Do we see a phi 3? Yes, we see a phi 3. What is being multiplied by phi 3? Minus 1 by 3 factorial. So minus 1 by 3 factorial comes here. We don't see a phi 4, so again a 0. We see a phi 5. What is being multiplied? 1 by 5 factorial and so on. So this is how you can expand sine in terms of this basis. Is that clear? So in this case, the basis in this example, which is the basis? Which is the basis? The basis is phi n of s, which is equal to s to the power n, where n is equal to 0, 1, 2. It's an infinite basis. And which is the linear vector space? Which is the linear vector space? Linear vector space is all the functions of s which have a Maclaurin series representation. All the functions which have got a Maclaurin series representation, those will be the members of this linear vector space. Okay, so all the functions which have got a Maclaurin series representation, they belong to a linear vector space which is spanned by this particular basis. Is this clear? Third example, that's a different example. It's about an electron spin space, a vector space whose members are spanned by the basis alpha and beta. Alpha and beta are two different spin states, orthogonal spin states. You could use this in a quantum field theory. A problem like this could arise. Okay, so we have we need to identify all those states which are having these two orthogonal spin states. Okay, so these are linearly independent or orthogonal spin states. So possible spin states are, this could be one spin state a1 plus alpha plus a2 beta, or b1 alpha plus b2 beta, or alpha and beta, they are multiplied by, instead of real numbers, they are multiplied by complex numbers. Okay, so that's your electron spin space. So your basis could be anything. Okay, that's the key point that you can take here. So we have seen three examples. One example, we have taken a finite set of Legendre polynomials that becomes a basis. In this example, we have a finite set of functions that becomes our basis. And in this case, third case, we have taken something called as a physical state, which is a spin state, to represent our basis. Okay, so basis can be anything, any state which is any set of states which are linearly independent, that can form your basis. So in this context, now we come across three theorems, three very important theorems. Okay, always keep these theorems in mind. Okay, what are these three theorems? The first theorem, what it says is a vector space. Okay, if a vector space V has any basis containing a finite number of vectors phi I. Excuse me once. All right, coming back to this one. So we have, suppose a vector space V has a basis containing a finite number of vectors phi I. Okay, then every other basis also contains those many number of vectors. Okay, to explain this, for instance, let us say I take three-dimensional space. So which is your linear vector space? Linear vector space. Okay, let me do it up here. So the linear vector space will be all vectors in 3 dimensions. All vectors in 3 dimensions. Okay. So what are the possible bases? Okay. What it says is, if any basis has got a finite number of vectors, then every other basis also contains the same number of vectors. So let us say one basis in Cartesian coordinates. In Cartesian coordinates, we have this basis, right? X cap, Y cap, and Z cap, right? So here, what is the number of vectors? How many elements are there in the basis? There are 3 elements, right? 1, 2, and 3. 3 elements are there. Then if you choose some other basis, can you think of some other basis? Yes, of course. We could think of spherical polar coordinates, right? In spherical polar coordinates, what will be the basis? It will not be x cap, y cap, z cap. It will be r cap, theta cap, and phi cap, right? This is another basis. This is one basis. This is also another basis. So in this case also, the number of elements in the basis is 3. What about cylindrical polar coordinates? In cylindrical polar coordinates, what will be the basis? It will not be x, y, z, or r, theta, phi. It will be rho, theta, and z. This will be the basis in cylindrical polar coordinates. Here also, how many elements are there? How many vectors are there in the basis? 3. Okay, so that's what it says. If there is, in a vector space, there is a basis and that basis contains n number of vectors, then every other basis also contains the same number of vectors. It's not possible that in Cartesian coordinates we have 3 bases, but in spherical polar coordinates we have only 2 bases, and cylindrical polar coordinates we have 4 bases. That is not possible. In every other basis, there will be 3 vectors. Okay, so that's your first theorem. Okay. Next theorem, if a vector space V has any basis containing a finite number of terms, same finite number of terms, then every set of n linearly independent vectors is a basis. Every set of n. So we have x cap. So we have x cap, y cap, and z cap. This is a basis. Here x cap, y cap, and z cap, they are all linearly independent. Okay, so it's like this. So this is your x cap, this is your y cap, and this is your z cap. Okay, they are linearly independent. But what about some other basis? So let's say if I choose this one, some other basis. Okay, let's say I add x cap and y cap. It is going to give me this one. This is going to give me x cap plus y cap. Let me use a different color. So let us say I add x cap and y cap, and this is going to give me this one, this vector. This is x cap plus y cap. And then if suppose I take in the other direction, x cap in the other direction, okay, minus x cap, this is minus x cap. And if I do minus x cap plus y cap, or y cap minus x cap, okay, so we'll get this one. So this will be y cap minus x cap. And then z cap will keep it just the same. Z cap will keep it the same. Okay. Then here in this case, here these 3 vectors, x cap plus y cap, is perpendicular to y cap minus x cap, y cap minus x cap, and z cap are linearly independent. Okay, x cap and y cap, these two are perpendicular, right? X is perpendicular to z and y is also perpendicular to z, and we see that this one, x plus y and y minus x, they are also perpendicular to each other, and because z is perpendicular to the plane which contains them, z is perpendicular to both x plus y and y minus x. So that means x plus y, y minus x and z, they are also linearly independent. You cannot express any one in terms of the other two, so they are also linearly independent. So what the second theorem says is, it need not be that only this is the only basis. You can take any linearly independent set. For instance, this is a linearly independent set. So here, x cap plus y cap, comma, y cap minus x cap, comma, z cap is also a basis. This is also a basis for this linear vector space. So this is another basis. So we have this basis. I added one more to this list, that is x cap plus y cap minus x cap and z cap. This is also a basis, and here we have seen n is equal to 3. It has to be 3 as per theorem number 1. So that's your second theorem. And the third theorem, it says, one second. The third theorem, it says that same, if I have a vector space which contains a finite number of, whose basis contains a finite number of vectors, there can be no more than n vectors in any linearly independent set. So this is actually follows from theorem number 1 and theorem number 2. Theorem number 1 says that every basis contains exactly n vectors. Theorem number 2 says that every linearly independent set is also a vector, is also a basis. Third theorem, it says that you cannot have more than n vectors in any linearly independent set. So that's the three theorems for on basis. Okay, it's important that you remember these three theorems. Okay, as statements of these three theorems, you should remember. Then this number that we have, right, this is a special number which appears in all the three theorems. Okay, first theorem, second theorem, third theorem, in all the three cases we have this number. You can see here, if the basis has got n finite number n of vectors, then every basis has got n vectors. Every set of n linearly independent vectors is also a basis. There cannot be more than n vectors in a linearly independent set. So this number n is special in case of this finite set with finite basis. Okay, so this is known as the dimension. This number n is known as the dimension of the vector space. Okay, so if you ask what is the dimension of the vector space, all you need to do is count the how many vectors are there in the basis. The number of vectors that are present in the basis, that gives the dimensionality of the vector space. So in these examples that we have here, what is the dimension of this vector space in this case? What is the dimension? What is the dimension in this case? Here, what is the linear vector space? The linear vector space is all the functions which have a quadratic form. All the functions which have got a quadratic form. That's a linear vector space. So what is the dimensionality of that vector space? The dimensionality is 3, right? Because how many elements are there in the basis? 1, 2, and 3. So just count how many vectors are there in the basis. That number is going to be the dimensionality of that vector space. So here the dimensions are 3, 1, 2, and 3. Next example, what is the dimension of this vector space? Anyone? What is the dimension of this vector space? Anybody? Calvil star. Are you there? Please unmute yourself. What is the dimensionality? What is the dimension of this vector space in this example? Calvil star, are you there? Desanchi, are you there?
Yes, sir.
Yeah. What is the dimensions of this vector space? Example number 2. What's the dimension? Anybody would like to help her?
And sir,
How much?
it has n dimensions, sir.
No, it's infinity. It's infinity. Because you see the basis, how many members are there in the basis? Phi n, how many values, how many possibilities are there? How many possible values of n are there? Infinity, no? Infinite n values. So the basis has got how many members? Infinite number of members. So this is an infinite dimension vector space. Understood? Have you understood this? There are infinite number of basis members. Okay?
Yes,
This
sir.
example, okay. This example, what is the dimensions? Just count the number of vectors in the basis. Can you identify the basis? Can you identify the basis? Desanchi, which is the basis in this example?
So alpha bar and beta bar.
Okay, so how many are there? How many vectors are there in the basis? How many vectors are there?
2, sir.
2. So what will be the dimension of this vector space?
Sir, it will be 2.
It'll be 2. All you have to do is just count how many elements are there in the basis. Okay, how many vectors are there, not elements, how many vectors are there in the basis. That's all. That will give you the dimensions. Okay, so please remember, memorize these 3 theorems. Okay, so this is the dimension. So how do you find out the dimension? Is the number of vectors in any linearly independent set or in any basis which spans the vector space V. So that is going to give you the dimension. Okay, so if a vector space has got a vector space with finite n, it's a n dimensional vector space. If it is a non-finite value of n, then it's an infinite dimensional vector space. So it's possible to have an infinite dimensional vector space. Okay, so now representation of vectors. Okay, so given a vector, so suppose I have a vector space V, and in this vector space V, we have a vector Y, and this vector space is of dimension n. Okay, this vector space is of dimension n, and it is spanned by a certain basis. The basis is phi. Okay, then we can write this y in terms of the basis. This we already know. Remember the Einstein summation convention. Here, which is the dummy index? The dummy index is I, because I is repeated, so it is understood that this is actually summation over I, eta I, phi I. This is understood. Okay, but we don't put the summation here. We just leave the summation aside and just put it as eta I, phi I. It is understood because I is it's a dummy index, so it is summed over this. So y is equal to eta I phi I. Then these coefficients eta I, they are known as the components. These coefficients eta I, they are known as the components of this vector. Components of this vector V in the vector space. Components of this vector Y in the vector space V. Okay, so these coefficients. So just like your when we say in vectors, no, 3-dimensional vectors, right? If I say a vector A, this vector A will have components, right? The components is AX, AY, and AZ, right? So what do they do? You take this component AX, you multiply with X cap, you take this component, multiply with Y cap, and you take this component, you multiply with Z cap. Multiply this with Z cap and add them together, that gives you this vector. So these are the components. In a similar way, we saw some time back this example Fs, right? We were able to write this as, let's say 2, 1, minus 1, right? So what does this mean? It means 2 P naught plus P1 minus P2, right? So these are your components. Multiply with the whatever coefficients you multiply with the basis vector, those coefficients which you multiply, they are known as the components of the set of such coefficients is known as the component of that particular vector. Okay, the set of components, okay, if I put them inside this is known as a representation of the vector y in the basis in this given vectors. So we really don't need to worry about, because we already know what the basis is. So because we know what the basis already is, we really need to know, the only thing that we need to know is these components, the set of components. Okay, so this is one representation, one such representation is known as the column representation of vector y. So actually, what is vector y here? What is this vector y? Vector y is simply, it is understood, eta 1 phi 1 plus eta 2 phi 2 and so on, eta n phi n. This one is understood, but because we already know what is phi 1, phi 2 and so on, that's why instead of writing it like this, we might as well just collect all these components, eta 1, eta 2, eta 3 and so on, and put them as a column matrix. So we can do that. Okay, so this is a column vector representation of the same vector in the vector space, which is spanned by the basis phi. Okay, okay, so let's say I have two different distinct bases. Okay, remember these three theorems. It is possible for us to have a vector space which has got many bases. I showed that example also. Three-dimensional space, right? Three-dimensional vectors in three-dimensional space. They can be represented either by Cartesian coordinates, the bases in Cartesian coordinates, or the bases in spherical coordinates, or the bases in cylindrical coordinates. So you could have multiple different bases. Okay, that is possible. So let us say I have two bases, phi and omega. These are two different bases. Phi 1, phi 2, phi 3 and so on. Omega, which is omega 1, omega 2 and so on. These are two distinct bases. Okay, in an n-dimensional vector space, n-dimensional finite number of dimensions. So it could have multiple number of bases. Only thing that we need to keep in mind is all the bases will have the same number of vectors. Okay, so that's why. So we have these two different bases which span the same vector space. Suppose the components of this vector y, any vector y, is eta I cap and eta I in omega. Okay, so this is what I mean by this. So eta I cap is the component in this vector. So what does this mean? It means, it implies that this vector y, okay, this vector y can be written as eta I prime times what are the members of this, what are the vectors which are inside this basis. The vectors which are inside this are phi I. So it can be written like this. And this is also another basis, and these are the components. These are the components. So what does this imply? It implies the same vector y. It can be written as these coefficients, these components times the members of this one. That is eta I into omega I. So that's what this means. Okay. So suppose the components of this vector be in this vector space, it is eta I prime, and in this vector space it is eta I. Okay, so this is the case. Then we have this one. Both of them must be same because they are the same vectors. Okay, eta I, this eta I prime into phi I is equal to eta I into omega I. Both of these should give me the same vector. Okay, so both of them must be the same. Now you see, omega I itself is a vector, right? An example of this is, because omega I itself is a vector, that means this omega I can also be written in terms of this phi i's, right? So we can write it like this. Omega I can also be written in terms of phi I. We can write it like this. An example of that is in your course on electromagnetism, you would have probably used the book by Griffiths, right? So Okay, I'll have to search for that book. So in your course on electromagnetism, you would have, in your BSc, you would have probably done this book, studied this book by Griffiths, Introduction to Electrodynamics. And over there, there is in the appendices, one of the appendices, they give a relationship between spherical polar coordinates and Cartesian coordinates, the unit vectors, right? So you can write down r cap, theta cap, phi cap in terms of I cap, j cap, k cap. You can do that, right? So that means you're writing the members of one basis in terms of the members of another basis. Is that clear? So this is what I'm trying to do here. Omega I, it's a element, it's a vector in this basis. Omega I is a vector in this basis. And because this itself, omega I, every member in a basis will be a member of the vector space itself. Okay, every member in a basis will be a member of the vector space itself. So it means every omega I can be written as a linear combination of this phi. Okay, every omega I can be written as a linear combination of these functions. So that's why I'm writing as omega I is equal to tau ki into phi k. Okay, I'm putting two indices because we have many different omega i's. So for each omega I want to identify it. So that's why I'm putting an I here, and I want to use a different index because there has to be a summation. Okay, so what does this mean? It means there is a summation here, which is the dummy index. Dummy index is k because the index which is repeated, that is the dummy index is k. So what this means is tau ki phi k. Because this k is a dummy index and it is repeated, the summation is over k, not with I. Okay, so we are summing over this one. So that's the reason why we are able to write it like this. Okay, so it means every omega I, every vector omega I can be written in terms of this. So therefore, you can use equation number 2 and equation number 1. So all you need to do is this omega I, you replace it with this one. Okay, so we have eta, you see this is a dummy index. Okay, I is a dummy index. So if I is a dummy index, I might as well replace I with anything else. So this is what I have done here. This is what is being done here. So in equation number 1, so we had eta I prime phi I. This is equal to, we had eta I, and omega I is nothing but tau ki phi k. So now what we can do is on the left hand side, this I is a dummy index. Dummy index means you can replace it with anything. So I'll just replace it with k. So eta k prime phi k is equal to eta I tau ki into phi k. So that's what we got here. Okay, is that clear? Once that is done, then this phi k will get cancelled. This will get cancelled. And finally, what is left behind is eta k prime is equal to tau ki into eta I. Okay, eta k prime is equal to tau ki into eta I. So this equation number 3, it is a relationship. It gives it a relationship because you can see what are these eta prime and eta. Eta prime are the components in one vector space and eta are the components in another vector space. So we have components in one vector space and components in another vector space. This gives us a direct relationship between these two components. So in other words, this gives us a way, this tau values, this tau ki, it will give us a way to transform from one vector space to another vector space. So this is, and this has got two indices. It has got two indices, k and I. So because it has got two indices, so this tau can be represented as a matrix. So that's why this is our transformation matrix. Okay, is this clear to everyone? All of you? Is this point clear? What we're trying to achieve here? Let me repeat once again. Eta I prime, these are the components, in the vector space. These are the components These are the components with respect to the basis, phi, and eta I. These are the components with respect to the basis omega. Okay, I'm writing omega, capital Omega. Okay, so these are two different bases. This is one basis, this is another basis, and these are the components in these two bases. And what is the relationship between these two components? The relationship between them is this: eta k prime is equal to tau ki into eta I. And where did we get this tau from? We got this tau from here. Okay, we wrote this tau from over here. So this tau, how many indices does it have? It has got two indices. So one is an index along the rows, and another one is the index along, sorry, one is the index along the rows, and another one is index along the columns. So your tau will be basically this tau ki's. It will be basically a matrix. So that's a transformation matrix. So it allows you to transform. If you know the components in one basis, using tau ki, you can find out what are the components in another basis. So in other words, it allows you to go from one basis to another basis. So that's why it's called as a transformation matrix. Understood, everyone? Is this clear? Larry, Mehtab, Mehul, Sensil, is this clear?
Yes, sir.
Okay, great. Okay. So this is what we have, the components of components. So here we were writing in terms of K and I, but it's better if we just replace K, I replace with I, and I replace with J. Okay, so if I do that, this is what we had. Okay, let me write this down first. So we had, I'll just write down this expression. So we had eta k prime is equal to tau ki eta I. So what I do here is this k I replace with I, and the I will replace with J. I will replace with J. So wherever there is I replace it with J. So this I here, and there's another I here, I will replace it with J. Okay, and wherever there is K, I replace it with I. So there's a K here and there's a K here. So I'll replace it with I. And when I do that, it is the expression that we get. Okay, eta I prime is equal to tau ij into eta j. Okay, so this can be arranged as a n cross n matrix. Because why n cross n matrix? Because I, what are the values that I can take? The values that I can take will be, from 1, 2, 3, all the way till n. And the values that j can take will also be 1, 2, 3, and all the way till n. Why? Why do I and j take the same range of values? Why do I and j take the same range of values? The reason is because phi and omega, they are two different bases. Phi and omega are two different bases, and according to theorem number 1, if one basis has got n number of vectors, then every basis will also have n number of vectors. So phi and omega are two different bases. If any one of them, phi, let's say, has got n number of vectors in the basis, then omega will also have n number of vectors. So that's why I and j, both of them, okay, I and j, both of them will contain n. So this tau ij can be arranged in the form of a n cross n matrix, and we designate this as T. Okay, so we designate this tau values, we designate as T, T11, 12, and all the way T1, and T21, T22, and so on, all the way till here. So this T is said to be the transformation matrix. If you want to transform from one basis, so this is one basis, and this is another basis. So if you want to transform from one basis to another basis, so we need to use a transformation matrix T. Is that clear? Is that clear? Okay, so we can write y prime. We can write in one basis y prime the other basis, it is y. So the transformation is simply t into y. So that is going to give us the vector in this one. And remember this one, this y can be written as a column matrix. So you can see here y prime. Y prime is a column matrix, right? And T is a n cross n matrix. Column matrix means this is n cross 1, right? N rows and 1 column. This is n cross n. And what is y? Y is also a n cross 1. You can see the multiplication, the rule of multiplication. The number of rows, number of columns in the first matrix and the number of rows in the second matrix must be same, which it is. And what is left behind is n cross 1. So you will get an n cross 1. Okay, so you will get y prime. Is that clear? So if y prime is equal to ty, then what is y equal to in terms of y prime? What is this equal to? T inverse, right? So if you want to go the other way around, we should be using T inverse. So this is the important criteria. This T, this transformation matrix that we have, it must be invertible. We should be able to invert this matrix. Are all matrices invertible? Invertible means the inverse of that matrix exists. Do all matrices have an inverse? Who can tell me? Do all matrices have an inverse?
No, sir.
No, sir.
No, right? Which matrices have an inverse? How do you check whether a matrix has an inverse or not? How do you check?
If the determinant is not 0.
Very good. If the determinant is non-zero. So the condition is the determinant of this transformation matrix, it must be non-zero. Very good. Who said that?
Me, sir.
Larry. Okay, goodbye. All right, so suppose I have an example, okay, of such a transformation matrix. So suppose I have a vector A which has got a following representation in Cartesian as well as spherical coordinate system. So this is a representation in Cartesian coordinate system. Okay, this is the representation in Cartesian coordinate system, and this is a representation in spherical polar coordinate system. Spherical polar coordinates. Okay, so Cartesian coordinate system, what is the basis? Cartesian coordinates, what is the basis? The basis is x cap, y cap, and z cap. And spherical polar coordinates, what is the basis? The basis is rho cap, theta cap, and phi cap. This is the basis. Okay, so you are going from one to another one. So there is going to be a transformation matrix between the two. And which is this transformation matrix? This is the transformation matrix. This is the transformation matrix from spherical to Cartesian basis. Okay, from spherical to Cartesian matrix. So which means if you know the components, if you know these components, if you know this a rho, a theta, and a phi, that is, if you know these, you can find out what are ax, ay, and az. You can find out what is ax, ay, and az. That is this one, using this matrix. So just multiply this matrix with these components, that is going to give us this. Is that clear? Is this clear to everyone? These set of numbers multiply with this transformation matrix, that is going to give you the corresponding components in Cartesian coordinates. Okay, everyone? Are you clear on this? By the way, if you want to have this transformation matrix, I think in your course on classical mechanics, I think you should be having this transformation matrix. Just check on once, okay? In your classical mechanics course, probably this transformation you'll be able to see over there. Okay, so this same transformation matrix from, and at least I think in Griffiths also it may be there. Griffiths Introduction to Electrodynamics. in the appendix, one of the appendices, it might be there. Okay, so you can just try it out, see for yourself. This is how you can transform from one coordinate system to another coordinate system, or one basis to another basis. So that's your transformation matrix. Is this clear to everyone? Any questions do you have? Any questions? Anybody? Okay, so if there are no questions, then I think this will be a good time to stop, because I'm getting a feeling that I'm beginning to overwhelm all of you, because we have had 2 classes today. So let me stop here.